Karl got his PhD from MIT in experimental nuclear physics. After being a postdoc of LBL, then he became an assistant professor of Stanford, and then after that, he moved to the Lawrence Livermore Lab as the founder of the high energy group and also in accelerated technology over there. However, he didn't stay there permanently. In 2009, then he became the vice president and the dean of research of the Naval postgraduate school in Monterey, California. Then in 2012, then we are very fortunate to have Karl back to Berkeley as the professor and now the chair of the Department of Nuclear Engineering. Now, Karl has received quite a number of honors. He is a recipient of the Sloan Fellowship, the DOE the Deputy Secretary Award for the B Factory when he was at the Livermore Lab, and also the Navy Superior Civilian Science Award. And also, he is a fellow of APS and also the AAAS. So today he is going to tell us about the search for the Axion. So let's welcome Karl.
Delicately pointed out, I've not been able to hold down a steady job. I think this year I'm an engineer. So I'm going to talk to you today on a topic, well, to be honest, an obsession that has sort of consumed me for about 30 years, and I think we're finally making some traction on, which are experimental searches for the Axion. And in fact, it's going to be, as you see, somewhat limited. The field, I think, is actually growing marvelously, and there's some I think wonderful developments, theoretical and experimental, going on in this department for low mass string-inspired axions as well. But I'm going to confine my discussion to the traditional Paget-Quinn axion viewed through the window of the axion-photon coupling. So what I will attempt to do in about 50 minutes before I have to go teach is I want to develop some intuition about the axion, because it's a bit of a strange bird. It's not a particle, if it's a particle, that would have evolved thermally at the time of the Big Bang. And it requires, I think, a little bit of discussion to give some physical insight for the axion, how it came to be, its cosmological relevance, and so forth. And then I'm going to talk about a kind of three variations on a theme, which are the search for cosmic axions, the microwave cavity experiment, and then laboratory experiments and solar axion experiments, all viewed through the prism of the axion-photon coupling, which has been, so far, I think, a quite fruitful way of looking for the axion, absent the fact that we haven't found it yet. I've been provided both with a laser pointer and a stick, which I requested because there will be two laboratory demonstrations during the talk, being an experimental talk, for which the stick is important. So let's talk about the axion, the unsung axion. Most, I think, modern students probably have not heard about it or heard about it only vaguely. Normally, it comes up, if they've heard about it, they've heard about it through the context of its possible role as the dark matter of the universe, and therefore what they've heard has not been encouraging. For many years, I'm reminded of the old Avis campaign, "We're number two, but trying harder." I think even to this date, it's been outflanked by a clean factor of 10, both in funding, personnel, and number of experiments by searches for the WIMP around the world. But I think we're gaining some traction here. I have to imagine that this department is suffering from dark matter fatigue, given so much of the leadership of the world's premier experiments in dark matter are situated here. So the only thing I'm going to mention, which I hope is familiar to everyone, is that we live in a universe that we now know is dominated by the dark energy, a problem that I think the students of your students of your students will probably not likely crack, and a more tractable problem, which is what is the identity of the exotic dark matter, the non-baryonic dark matter, which makes up about a quarter or a third of our universe. But it is important to bring this up, both because of one context, we'll look at the Axion, and also in the approach I'm going to give to developing some intuition about the Axion. So let me try something. I'm quite enamored by this. Our colleague Pierre Sakivi at the University of Florida, just a wonderful theorist who's had so much to do with this field in terms of the physics of the Axion, the cosmological sense, the cosmological implications of the Axion and Axion searches, I think developed a very nice kind of allegorical approach that was published 20 years ago in Physics Today. So let me attempt to reprise his sort of little allegory or fable to developing some intuition about the Axion. And so the story goes is there's a group of graduate students who, in their spare time, their recreation is playing pool. Now, what's interesting about this, they've just ordered a pool table. By the way, most unusual thing, these are not graduate students on Earth, they're graduate students on Mars. And they've just ordered a pool table from planet Earth. It's been shot over in a rocket ship for 20 months before landing on the Martian surface. This is a catalog, off-the-shelf pool table, one size fits all, that is plunked down on the Martian surface, and the students go about happily playing billiards. Now, there is a heavy curtain that you cannot see, and being colorblind, there's a laser pointer I cannot see, which is obscuring the underside of the table. And the most clever of the students, who Pierre calls TSP, the thinking snookers player, is not content simply to play billiards, but asks himself, how is it that a one-size-fits-all, off-the-shelf catalog pool table plunked down on an arbitrary part of the Martian landscape is flat to 1 part in 10 to the 11, such that you can play an honest game of pool? And his less astute colleagues are not even bothered by this question. Because the Martian surface, just like Earth, is contoured, and you have 2 vectors everywhere. You have the local gravitational vector, and then, since this can be on the side of a hill or whatnot, there's also the local normal vector, and there's an angle between them, which does not need to be 0. In fact, in general, will not. So TSP formulates a hypothesis, and the hypothesis is, he said, if I were a manufacturer of pool tables, what I would do would be to make a pool table on a pivot with a very long lever arm, unprescribed in length, but sufficiently long, and a heavy weight on the end. Can't miss. No matter where you put it down on the Martian surface, the thing is going to become level. And of course, this immediately suggests an experiment, which is kind of the paradigm for what we do in nuclear and particle physics, which is trying to promote a quanta out of the vacuum. He smacks the ball with a pool cue against the bumper, and if his hypothesis is correct, he should be able to see an excitation of an oscillation of a particular frequency there. The experiment fails. But TSP does not get discouraged, reasoning that, of course, that if the lever arm were sufficiently long, one should not expect that such a puny impulse would lead to a visible excitation of the table. Now he has the critical insight. So the pool table is en route from planet Earth. Pierre Sakivi, Belgian-born, actually said it was, in his article, shipped from Minnesota. And I asked him once about this. And I said, Pierre, what's with Minnesota? And the only thing he remembers from the movies is Minnesota Fats. He thought that all pool tables were manufactured in St. Paul, Minneapolis or something. Here, I think even an enterprising pool table manufacturer would say, well, in all the months I have of doing nothing, I could even assemble a thing from a kit. In the weightless environment, when the thing is coming over, you have, again, two vectors. You have the body axis of the rocket ship, and there's the body axis of your pool table, which may or may not be aligned with the body axis of the rocket ship. And so you have an angle in the problem with no physical significance. Now, the critical thing is, at the time when the rocket ship comes to Mars and fires its thrusters and begins to slow down, if you're an astronaut sitting in the rocket ship, you go from a weightless environment, and as you fire the thrusters and it slows down, it settles down, you adiabatically feel the local gravitational field turn on. You go from 0 up to the local G of the Martian gravity, and now an angle here, any offset angle becomes terribly important. The pool table now says, I'm out of position. And what happens is that, of course, you end up with a damp-driven oscillator, and the axis of the pool table begins to oscillate around the minimum theta equals to 0, which leads to a flat pool table. And so TSP says, I now know what to do. I'm going to look for the relic oscillations in the pool table. Just as an aside, I was amused when I was, to sort of carbon-14 date myself, when I was a young kid, Flash Gordon and all that, all rocket ships, all proper rocket ships landed by firing their thrusters and landing butt end downwards. Then, of course, we had, the Soyuz and the Mercury and the Apollo program and all that, and all proper rocket ships now just sort of parachuted down into the ocean or into the snow or something like that. Interestingly, Elon Musk, who's now teaching us how space travel should really occur economically, now has his rocket ships landing butt down and they're recoverable. So it's interesting to see all things come back full circle. So what TSP does now, he says, now if I really want to do a sensitive test of my hypothesis, what I'm going to do is build a very high Q oscillator and then tune the frequency of that oscillator by changing the spring constant in small steps or changing the mass in small steps. And if my hypothesis is correct, then at some point, I don't know what the remnant oscillation frequency is in the table, but if I'm lucky, I will troll at some point and then see an oscillation about this frequency, this Lorentzian here, of the unknown omega naught, and he will have proved his hypothesis. This is also the tip-off of the experimental avenue for looking for the axion in the microwave cavity sense. We're going to couple the axion field to an electromagnetic field, as I'll describe shortly. And the way of looking for very small oscillations by coupling them to high Q oscillators is an old and venerable paradigm in physics. I think many of us remember studying the book of Roginski back in the 60s. I think it was called The Role of High Q Oscillators in Fundamental Physics or something like that, where this theme is played again and again. And I remember my Stanford days, Bill Fairbank with his large, super-cooled 10 millikelvin aluminum bars for gravity wave detectors were coupled to a little drumhead, very, very thin drumhead, that was to play the same role, and then a little squid amplifier there, looking for the oscillations sloshing from the large bar, immeasurably small, into this little drumhead. So now, the only small technical business here, and this will be sort of extremely broad brush. We have the theory of the strong interaction, which has one offending term, which violates CP symmetry, charge conjugation and parity, the product operation. And in principle, there is a unprescribed parameter there, theta, plays the role of a phase, which has no particular reason to be any particular value. And for any value, order of magnitude unity, that you expect between 0 and 2 pi, would give rise to measurable neutron electric dipole moments on the order of 10 to the minus 15 centimeters or so. Now, problematically, since the early 50s, Norman Ramsey and experiments unbroken since then have driven that number down to immeasurably small numbers, on the order of 10 to the minus 26. I think I've corrected that. So this parameter theta, in fact, properly theta bar, theta minus another unprescribed parameter in the standard model, has somehow hit the magic number to 1 part in 10 to the 11th, suppressing strong CP violating effects. And this begs the question why. You could say this is a fine-tuning problem, just like people are happy to play pool on a level pool table, or you could say there's some dynamical reason. Petchan Quinn in Stanford in the late 70s conceived of a very elegant model by which theta becomes a dynamical variable. At some high temperature, the theory, theta there's a symmetry breaking by which every point in space picks out a value of theta, continuously connected. And again, here you have an angle with no particular physical significance. Long after the Big Bang, 100 nanoseconds after the Big Bang, at QCD time, the universe cools down to GeV temperatures or so, and now you see this infinite multiple vacua, this sort of washboard potential here of QCD. Theta now says I'm out of position, and this theta field begins to roll around the CP conserving minimum. Voila, the solution to strong CP. To this day, Roberto slaps his head and he says, we were fools. We got 95% of the way there, and literally within weeks, Frank Wilczek and Steven Weinberg independently realized that this sloshing of the field was a physically manifest particle that they termed the Axion, and then set the experimentalists forth to go find it. So let me complete the Axion, the analogy, the allegory here, and just give some basic phenomenology. The Axion is like a very light cousin of the pi zero. First of all, both the mass and all its couplings are inverse to F. So this large unprescribed symmetry breaking scale F, think of as the length of the lever. As the longer the lever is, the lower the frequency of the oscillation. The higher the symmetry breaking scale is, the lower the mass. Similarly, if the lever gets longer and longer, TSP discovered he could not excite the pool table. Similarly here, for the symmetry breaking scale getting larger and larger, all couplings, including the Axion photon coupling, are suppressed like 1 over F. More interestingly, we have a limit from cosmology. At sufficiently large values of the symmetry breaking scale, i.e., or sufficiently small values of the mass, you have an overclosure problem. And we know we don't live in a universe like that. Just as for a given offset angle, a longer and longer lever arm implies a larger stored energy in the pool table. So the analogy, this allegory holds up exceedingly well. I think Pierre has given us a very good way of thinking about the Axion. We have limits on the Axion from the supernova, 1987A, axions from nuclear and bremsstrahlung above about 10 millielectron volts would have quenched the neutrino pulse, and we know that didn't happen. We got just this beautiful signal, 20 or so neutrinos distributed over about 10 seconds, just in accord with all core collapse models. Ordinary stellar evolution sets limits on the Axion. And so we're left with a situation, which is kind of a good news, bad news story. We have a bounded parameter space. Problem is, where that parameter space is just dismally weakly coupled, and therefore we're going to need some very clever ways of looking for the Axion. Now, you might ask the question, gee, if axions are the dark matter, this should be duck soup. I could take any radio telescope, look out at anyone's halo, including our own, and you'll see a bunch of lines. A lot of them are sort of molecular lines, interstellar lines, or our own atmosphere, and those you know, but you may find a line that might be broad to 1 part in 10 to the 6 and of unidentified frequency, and a point you could say, aha, that is half the mass of the Axion. Well, problematically, if you look at the relationship between the mass of the pion, 135 MeV, and the mass of the axion, where we think it is in some micro EV to milli EV scale to the 5th power, you find that these are dismal lifetimes. In fact, it would just be a hopeless task to ever see axions by looking at their spontaneous decay. Now, here is where Pierre helps us. Pierre reminds us of something we call the Primakov effect. This was his paper, Fizerov letter in 1983. It's a brilliant paper which really sort of invigorated the field. And he reminds us that a magnetic field can be modeled, or represented as a sea of virtual photons. And as such, an axion passing through a classical magnetic field can convert into a photon carrying the full energy, or vice versa. A photon coming through a magnetic field can convert back into an axion like that, with the magnet brokering momentum conservation. So you have, although it's a 2-photon process, in fact, what you have is an axion going into a single real photon, or a single real photon going back into an axion. And we now want to look at this thing in 3 contexts. Young students, and again, showing my age, say, who was Primakov? And this was Henry Primakov, Russian-born physicist at Washington University, later Penn, solved a problem in kind of, your father's high-energy physics, which was the problem, the early days of high-energy physics, what was the lifetime of the neutral pi 0, which was known to be extremely small, but no one had really a very clean way of measuring it accurately. And what Henry Primakov realized was that you did not need a clock to measure the lifetime of the pi 0, that if I took a GeV beam onto a thin target of a sufficiently high Z target, for example, gold, you can look at the conversion of the photon in the classical electromagnetic field of the nucleus, the fusion of a real and virtual photon, giving rise to a pi 0, which will decay almost immediately, and then you can measure that thing in a forward calorimeter. You don't need to measure the lifetime. All you have to do is measure the cross-section, because the cross-section and the lifetime are both connected through the common pion-photon coupling. And if you measure one, it's synonymous with measuring the other. So let's talk about the microwave cavity experiment, which are now, I think, there are now a lot of interest around the world. Several experiments, and depending on how you count, you might say already into the 3rd generation here. And basically, the microwave cavity experiment, as foreseen, envisioned in Pierre's 1983 paper, was nothing more than a car radio, but a very good car radio. And there are 3 essential elements. There is a very strong superconducting magnet, as large and as strong as you can make it, a high Q cavity, and then a state-of-the-art preamplifier like that. And what you're looking for is you mix this down, just like a heterodyne receiver, and you're looking at a power spectrum and looking for excess power in a narrow line, not monochromatic, but narrow to about 1 part in 10 to the 6th, due to the virial motion of the axion dark matter in the halo, 250 or 300 kilometers a second, so the breadth would be about 1 part in 10 to the 6th. The width would be about 1 part in 10 to the 6th. And so you're listening for this background noise, which is black body noise and amplifier noise, and you're looking for a weak signal above the background. So in a little more detail, the cavity, which you want to make as high a Q as possible, has its own bandwidth, of course, inverse to the Q. And the power is going like things that you do not control. Like pointers. The density, the local density, the mass, and the coupling constant squared. And then what is in control of the experimentalist, which is B squared V, proportional stored energy in the magnet, the Q of the cavity, the quality of the factor of the cavity, and the form factor, which I don't want to talk about, which is really effectively the overlap integral of, or the square of the overlap integral of the electric field and the uniform B field, which is really going to point out one mode in particular, the TM010 mode, like that. So the signal to noise is not simply an issue of power, it's a ratio of power over system noise temperature. And then of course the Dickey radiometer equation tells us that if you have a sufficiently, a receiver free of systematics, if I know where my signal is and I integrate long enough, I can tease the signal out of the background and the thing will tease up out of the grass with the square root of time. Not a good stratagem if you have to scan over 3 orders of magnitude in mass in very small steps. One really needs to boost the power up, and one really needs to drive the system noise temperature down. And the noise is really the sum of the blackbody photon contribution, and this is the amplifier, the equivalent noise temperature of the amplifier, which is subject, linear amplifiers are subject to the standard quantum limit. One cannot make an irreducibly low noise amplifier without, of course, playing some tricks, which we're beginning to noodle around with right now anyway. First generation experiments were done at Florida and Brookhaven in the late 80s with sort of coffee pot type experiments. These were masters, these were real pioneers that really set out the general strategy for how to do this experiment. They really laid the groundwork for what's sort of the definitive Axion experiment at University of Washington. Began at Livermore, was there for 15 years and moved up to Washington in 2010, called ADMX. And this really built on the experience of the first generation experiments, but this was a very significant scale up. That is a 6-ton magnet, about a quarter of a cubic meter sensitive volume, 220 liters. And at the time we put this together, we were enjoying a wave of developments in these transistor-based amplifiers, high electron mobility transistor amplifiers, and seeing the noise temperatures in the several hundred megahertz range, gigahertz range, drop from 10 to 5 to 3 to 1.5 Kelvin as these devices became better and better. But they got to a point where they were not becoming very much better. And we were still dealing with a physical temperature, which was 4 Kelvin, later pumped helium temperatures about 1.5 degrees. So we were dealing with a system noise temperature of about 3 Kelvin or so. Given the scale of the experiment, nevertheless, it did remarkably well and actually finally, for the first time, got down into cosmological sensitivity. I like to make the comparison here. I think this is a tribute to Les Rosenberg and his students, Les at that time at MIT, for having designed a receiver that was so systematics free that you could integrate for a month. And you saw the Dickey radiometer equation, you saw the signal to noise improve as the square root of time for a full month. So if you had sort of foreordained knowledge of where the Axion was, you could sit on it and actually see a signal as small as 10 to the minus 26 watts. I think it's 1/100th of a yoctowatt. And I remember talking on the phone once to a guy by the name of Larry Lasher, who was the project manager for the Pioneer 10, Pioneer 11 missions that were launched in 1972. And Pioneer 10 crossed outside of the orbit of Pluto, I think around the millennium. It had two 8-watt onboard amplifiers. One had conked out, the other was limping along, I think transmitting a power of about 4 watts. And the last signal we saw from it was in this large telescope, 70-meter telescope in Spain. The signal was about 10 to the minus 21 watts. We're looking for a signal that may be 1 or 2 orders of magnitude smaller. And of course, we do not know the frequency, and therefore we can only spend a few minutes at each frequency and then have to step tune this thing along. So I think that's a great tribute to the receiver that was made. Now, all that being said, we were in a sense of disquiet, because what was clear to us when we built this is it was like singing a song where you didn't know the second verse. We knew that if there was not some breakthrough that would occur on a time scale of about 5 years, this thing was going to come to a crashing halt. And the savior of the experiment was John Clark. Les Rosenberg and I put on a workshop here at Berkeley back in 1994, and John gave a beautiful talk on squids, which at that time were sort of these quasi-DC devices, wonderful magnetometers, but not gigahertz amplifiers. And he tapped us on the shoulder afterwards and said, if you can wring out a little money from NSF, for example, for one postdoc, I can deliver the goods. And in quintessential John Clark way, he under-promised and over-delivered. Literally 2 years after we got the money, I think Willie Chowsky was the NSF director of high-energy physics at the time. Tricia Rankin, now at Colorado, was the program manager that we convinced to fund this. Within 2 years, he gave us amplifiers which were manifestly quantum limited. They could be staged, tunable, and work with a reactive load. Everything we wanted like that. Now, at that time, DOE did not spring. They did spring for the upgrade. They did not spring for the refrigerator. But the promise of the squids, as seen on here below at least a gigahertz, is that you can see that if you cool the squid down sufficiently, one can get down within arm's reach of the classical quantum limit, an improvement about a factor of 40 over the conventional transistor-based amplifiers. And off we went, and the experiment has a wonderful future ahead of it. So there we were. This is circa 2010. And I remember giving a talk at Pierre's Festschrift, sort of a summary talk, and sort of we had a little community discussion. I said, this experiment is doing very well from the point of view of drilling down. And this may be the one dark matter experiment where sensitivity is not an issue, but the ability to troll is. We've not really broken above the gigahertz mass range, whereas really the smart money, theoretically now, are for axions that may be in the 20, 50, 100 micro EV range. But of course, who knows? By the way, I've given kind of the standard arguments for why the axion ought to be heavier than a micro EV cosmologically. There are, for now a number of years, I think a realization that string theories produce oodles of axions. Any realization of string theory probably gives rise to hundreds of scalars. They all tend to live naturally down in the nano EV range. There's very good reason for them to exist, and they're very good concepts. Peter Graham, Surjit Rajendran, Dima Budkar, and others are working on this experiment called Casper, which I'm sure they've told you about, to look in the range below. So I did not want to simply dismiss the interest in looking down below. So a bunch of us decided to form up and say, what we really need here is a very informal gang, sort of to make a little pathfinder and innovation testbed experiment, and to solve the problems for what life is going to be like in the next higher mass range, amplifier-wise, cavity-wise. Every time you go up a factor of several in frequency, you really do need to reinvent this experiment. There's lots of new problems. And this was agreed upon as good and wholesome by all. We recruited Steve Lamoureux at Yale and then built up an NSF-supported small platform there, which has now just produced I think in a very timely way, just in all the space of 5 years from a cold start, a very promising new physics result. So here's the team. I'm quite proud to say that all of my undergraduates and even one of my graduate students came out of the physics department here. In fact, on many areas of the research we do in nuclear engineering, we're very privileged to have your students work with us. Feel free to send them over, and they'll be very well taken care of. There's the technical design report. In fact, it was, I think it was anathema to think, well, ADMX is now a Gen 2 experiment under a heavy DOE project management regimen. There's quarterly reporting and change control boards and all this kind of stuff that was just completely inimical to doing a kind of a skunkworks, garage type experiment. So Steve Conrad and I basically managed this thing by telephone calls. That was the first, that's what the experiment looks like right now. That was the TDR, and I think it was on Steve's blackboard for about a year before we erased it. It looks like a somewhat smaller version of ADMX, but with some new features. Basically, we're now dealing with an annular cavity. We're using a tuning rod on a pivot, which is so large that, in fact, one could really just calculate this thing as calculate the frequency as more better described even as an annular resonator. We're using Josephson parametric amplifiers, which are very suitable and for the 5 gigahertz range, even up to 10, 15 gigahertz range. And lots of things that we've brought to the game, which are a little bit different from before. Lots of things when you commission a new experiment give you fits and have to be surmounted. There was a major campaign to reduce the fringe field from the main magnet, which was 9 Tesla, up where the amplifier resides. It needs to be brought down to the femtotesla level. And this required a defense in depth of active bucking coils, actually a series of 4 persistent 100-turn superconducting coils, 2 layers of cryoperm, a layer of lead sheet, superconducting lead sheet, a layer of niobium sheet, and what will go in next, actually, to improve matters a little bit more, is a niobium box around the JPA. But in fact, this worked marvelously. There's the flux bias for tuning of the JPA over about a 50% dynamic range and frequency. And you see red points interspersed with blue points. You can see the difference between having the magnet off and all ramped all the way up to 9 Tesla. It doesn't even hiccup. So in fact, we really have solved the problem of knocking down the field sufficiently to be able to do the experiment. Things that you don't think about, these kind of things that you slap your head and say, what were we thinking? There was a freak snowstorm in March in New Haven, and just at that moment, the central uninterruptible power on the Yale campus was out of commission, and it wreaked enormous havoc all across the campus, including our experiment when the magnet quenched. It really looked like a hand grenade went off. I'm now reminded again of the old, you remember John Cameron Swayze, the Timex watch commercials from the 1950s, where they would tape a Timex watch to Mickey Mantle's bat, and he'd, smack a line drive like this. And the jingle was, it takes a licking and keeps on ticking. Interestingly, when we looked at this disaster and pulled it out, the dilution refrigerator was still working. I mean, it was very delicate little capillary tubes and, sintered pots and so forth. I thought it would have been a complete wreck. Our engineer came over from Germany. He was astonished, but sort of giggled, and he put the thing back together with very much less bulk copper. If you're ever worried about a quench, be very careful to keep the amount of high conductivity copper down. Lenz's law and so forth. And away we went. And we only missed about 8 weeks of data taking. There was the data. We are very pleased with the quality of the data. It's manifestly Gaussian out to 4 or even 5 sigma, like that. We can inject synthetic Axion peaks of the right breadth and size and see them, fish them out of the data. And what we have just submitted for publication a month ago was a new limit now for this very small experiment. This is a cavity which is only about 1.5 liters in volume, compared to, for example, the ADMX, which is 220-liter cavity, which still gets down into the cosmologically interesting range. We did have some pesky problem we've identified as being the tuning rod being imperfectly thermally shunted that we have to work on. So at this point, we are only about 3 sigma over the 3 sigma times the standard quantum limit, whereas we should actually be much closer to the quantum limit. But we have a mitigation scheme for that. And I think one of the next steps, Conrad Lehnert has got a squeeze state receiver that we're going to be trying this spring. This is the whole purpose of the experiment, is a test bed where we could try things rapidly and agilely and fail early or make big, nice gains for the field of the microwave cavity experiment. Here at Berkeley, Berkeley is the cavity institution. Colorado is the the amplifier institution. Yale is the one ring that binds them all. This is the bane. One of the things that problems we're attacking is that here's the TM0N0 mode, the one with the largest form factor. The TM0N0 modes have some coupling to the axion. No other TM or TE mode does. But there is a thicket, an absolute forest of mode crossings. As you troll this, you move the tuning rod, you run across a forest of TE mode crossings, of which I'm only showing you the largest. In between each of those two, there are actually several much smaller ones. Some of them bothersome, some of them very bothersome, some of them not so at all. And this is really like, if you're going to do a wide dynamic range scan, this is like trying to sprint in a jungle, and it doesn't work. And so, in fact, we've actually demonstrated, and we actually have a bead perturbation set up there where we actually can look at the modes. And up at the top left, you see here's the TM0N0 mode, 8 megahertz away from a high order TE mode. And you can see it has the requisite flatness you expect there. But of course, then as you bring the thing into proximity with the mode crossing, it's just very much like standard quantum mechanics 2-mode mixing, Rydberg levels or whatnot. You can actually see that the modes hybridize. It's a mess, and you have to chop out a large section of frequency, and you're blind until you go and put in a cavity, different cavity that moves that crossing away. And so I was very pleased when I came here to discover, I've been thinking for years about photonic bandgap cavities, which are electromagnetic resonators with kind of a bundle of rods with a defect in the middle, which have been profitably used in accelerator physics and photonic structures to trap TM modes while allowing TE modes to radiate away. And when I came to Berkeley, I discovered I was just 50 yards across the street from Ilya Yablonovich, who was the father of this field, just received a very nice prize from the Royal Society, the Newton Prize, for his work in pioneering these photonic bandgap cavities. We're now modeling and about to build prototypes on this, where you see there was literally nothing in the spectrum, and now you can move that thing like on an open highway and then troll without interference. Let me talk about laboratory searches here. The next two things, and I'll be very brief here, are now in a context where we're looking at the axion or the photon with an energy much greater than the rest mass. And now I think the formalism, very nice, very reminiscent of neutrino mixing. There's a very nice axion-photon mixing formalism developed by Leo Studalski and Georg Rafelt. One can envision now taking a laser beam and shooting it down a high-energy physics dipole magnet, where the polarization of this is an E dot B interaction. The polarization of the photon of the laser is parallel to the B field, and you get out a beam of axions with exactly the same coherence of the laser beam. And it goes like so. Coupling constant, the length and strength of the magnetic field squared, and then a form factor, because of course the little awkward detail is in one case you're dealing with a photon which is a massless dispersion relation, and then a axion, which in fact is not quite massless, and this gives rise to this kind of mixing. If I have an arbitrarily long magnetic field, here at the photon state to the left of the magnet will begin to roll into the axion state, but at some point will restore like that. Now, for energies sufficiently high or masses sufficiently low, then of course you'll see a quadratic buildup of the probability of the axion as you lengthen the magnet. But of course, at some point you will run into trouble if that condition is not sufficiently well met. Now, this is kind of my debut in the field some 30 years ago. It occurred to me, I think, a very elegant way of looking for the experiment would make a symmetric arrangement where you would shine a laser through a magnet, put up a brick wall, and then have the axions reconvert into photons in a phototube. And several of us, I recruited some of my smart friends as theoretical bodyguards, and we published an interesting paper on this, where we conceived of how ambitious you could do, including putting something like 250 meters of SSE dipole magnets on either side of the wall. How far could you reach? And we realized that as hard as you push on this thing, it was very clever, but it was never going to be terribly competitive. Nevertheless, lots of people got into this business with a view to doing things more ambitious in the future, and have actually pretty much validated where we thought they would get stuck. Now, another one of these head-slapping moments, I think about 20 years later, I remember thinking to myself, we have been fools. There's an obvious way of making this experiment better. And the calculation is quite simple. If you put a Fabry-Perot optical cavity around the production magnet string and the reconversion magnet string, lock them, and then lock them together, you can boost the probability, if with a high enough finesse, with very good optical cavities, you can make the finesse 10 to the 5th or 10 to the 6th, to the finesse squared. So you can actually increase the photon-axion photon probability by factors of upwards of 1 trillion. Fourth root of that, the limit on G to 3 orders of magnitude. Now we're talking. Interestingly, some people have actually taken this quite seriously. There's a very serious collaboration now, a German-US collaboration based in Hamburg, that are now going to repurpose the old Hera dipole magnets, put them in a string, and try to get down below the horizontal branch star limit, which I think they should be able to do. They've got all the right people involved. They've got the Florida LIGO group and the Hanover group. So these are really the premier optics people who know how to do single photon detection by heterodyning. They know how to lock these cavities as one does in LIGO, Pound-Rieger Hall. They've got all the right people there. I wanted to show one thing which is quite amusing, and that is, this is so true to life in experimental physics. Where is all the risk? What's the most critical step and occupies most of the money? It's not the fancy stuff like the LIGO optics. Here's the second lab demonstration. When you build a high energy physics ring, you build these very long superconducting magnets, but you build them with a sagitta in it to most closely approximate the curvature of the ring. In the case of the Hera dipoles, which are almost 9 meters long, the sagitta is about 15 millimeters. That would be a disaster for having a very long, 100-meter long beam path where the optical mode requires the full 50 millimeters such that you're not clipping the beam at the level of more than about 1 part in 10 to the 6th. And so DAISY's role is this very delicate, very mundane and inglorious task of spending a lot of money in engineering to basically thumb screw the magnets back into flat. So, and they've actually done it. They actually did a test of this a couple of years ago and discovered they could do this without destroying the superconducting pack, and it works just fine. And now you can get the full 50-meter board to do this experiment. Final thing will be done. Another context of relativistic axions, and this again was envisioned in Pierre's paper in 1983, which was the fact that the sun's burning core should produce oodles of axions, and particularly axions in the EV range. The flux at the Earth's surface might be 10 to the 12th per square centimeter per second. And one can basically do the same trick, which is to take a dipole magnet and put it on a gun mount or some kind of other crane, point it at the sun as much time, day and night as you can, and then look for a hard X-ray spectrum with a mean temperature of about 4.2 keV. Central core of the sun's burning core is about 1.3 or so Kelvin keV, but plasma effects there basically suppress the axion emission at low energies, and the spectrum is hardened a little bit, but not too hard. You're looking really for a quasi-Maxwellian of about 4 keV mean temperature. The guy who was always fast out of the blocks was Adrian Melisinos at Rochester. He beat us to the punch. he had his own mafia down in building 903 at Brookhaven, his base of operations. And when he saw the Pierce paper and the paper we wrote about how to extend the thing to higher masses, he simply took an old warm magnet, 2 meters long, in this tin shed building. They kind of looked out the window and said, well, the sun is going to come down about there. They kind of went like this, and they kind of shuffled the magnet around. They put an X-ray detector behind it, went for coffee. The sun went down. They came back. There were no counts, and they published a preserved letter. My hat's off to it. The people who have really done this in spades, there was a very nice experiment at Tokyo and an even bigger one at CERN. That is a 50-ton LHC dipole magnet on a mount reminiscent of William Herschel's telescopes in the 1700s that tracks the sun morning and night for about an hour and a half each with, this is a 2-bore magnet, so you can actually put detectors of all types, front and back. In fact, true European collaboration way, you actually had 4 vested interests. You had the Germans and the Spaniards, and you had the French and someone else, each with their own different technology on one end of one bore, and they all worked very well. Again, you would not have gotten into the Peche-Quinn model band, but we had an idea some years ago that if you actually fill the magnet bore with a dilute gas, ideally hydrogen, but that's not good to play with, helium-4, and when you need to get to a higher vapor pressure, helium-3, you can actually tune that gas pressure in small steps and actually make the experiment selective at one particular mass where full coherence is restored for over arbitrarily long length. And I remember dealing with a vast number of lawyers, both from the lab and from CERN, when we shipped over a bottle of helium-3 that was worth $12 million, just when, of course, it was after 9/11 and everybody was paranoid about helium-3 and the supply and so forth. Not all of it came back, but it was for the good of science, and the statute of limitations has passed, so I think I'm safe. But with that trick of matching the dispersion relationship with this gas filling, they were able to push out helium-4 and helium-3, up here, into the Peche-Quinn model band. Now, this is mind-boggling. This is the aspirations that this gang has going forward, called EAXO. It is a prodigious experiment. That's a human being standing down here. The US contribution, if it comes to pass, and I hope it does, would be essentially the team that built the X-ray optics for New Star. It's an X-ray mission in space, taking data now for several years. Sort of slumped glass, Walter optics, parabola, hyperbola, with very fancy coatings on it. So this would be a MIT Columbia Livermore gang that would build these X-ray optics with something like a 5 or 10 meter focal length for each of the 8 bores of this thing here, which is nothing more than a stretched version of Atlas. I mean, this is really, these people are not any wanting for ambition. This is all, I think, beginning to move ahead rather nicely. Okay, let me wrap up here. This is where we are. This is what you see when you open the particle data book about axions, including the aspirations of ALPS and the EAXO here. You might say, well, if they, ALPS not at all and EAXO only up here, really only get into the kind of EV range of axions, what was the physics motivation? It turns out, this is a longer story I did not get into, lots of reasons for suspecting that there may be generalized pseudoscalars which are responsible for anomalous cooling of white dwarfs or anomalous transparency of TeV gamma rays coming across the universe, which should have been extinguished. But if not, one conceives that we might have produced axions or photons converting in galactic magnetic fields into axions, which are then transported transparently and then reconverted in our own galaxy here. So I think there were very good motivation and possibility of surprise for building these kind of experiments at all. ADMX and similar should be able to cover part of this phase space over many years. But my greatest fear is what I call the axion from hell, which is an axion at a very inconvenient mass of around 100 micrometer higher. And there's just simply not a good concept for that until recently. And there's now a fifth force type experiment, Stanford, Nevada, Indiana, Korea, called Ariadne. There, Orpheus is kind of an open resonator technique. You have Casper here being led by the Berkeley Mainz group, and sort of discrete LC circuits being pursued by Florida and Munich. So a lot of activity going on, and who knows, my comment there is that if the Cubs could win the World Series, who knows, someday we may find the axion. The most poignant thing about this, I remember being at a workshop in 1987 when Frank Wilczek was very enthusiastically saying, look, to hell with collider physics, we can do world-class physics with just a few good friends. And this was an exciting appeal to arms there, just saying, look, we can do tabletop physics and we can move the world. And this became particle astrophysics. But then you look at that and you say, what happened to my, I mean, this is now collider scale collaborations, hundreds of $millions. So particle astrophysics has kind of gone the way of all flesh as well. I think the rationale for our little test bed at Yale was this is a field that needs technical innovation, and one really does need to focus on something where you can try things quickly, agilely, fail early, maybe find some nuggets that really improve the game. And I didn't talk about it here, but if you really want, you know, as I say, the thinking person's dark matter is axions. I'm sorry, Bernard. It turns out being a total energy detector, if there is fine structure in the axion signal, you will see a very rich phenomenology of Doppler motion associated with the spinning of the Earth and the rotation of the Earth around the sun, which really gives you a field of astronomy. It really allows you to then uniquely point to the infall from discrete directions, the sort of the vector flow of the history of the formation of our galaxy. But I don't want to belabor that point. So, and as I say, if the Cubs can win the World Series, we may be in for a pleasant surprise. Thanks very much.
In a few minutes, so let's leave the question.
Congrats on the great results. What's next for the Yale, Colorado, Berkeley apparatus?
We're reestablishing operations to show that we've actually mitigated this sort of trapped heat in the tuning rod. I think that will be successful. The test is going on right now. Conrad has got on the bench something he published already several years ago, but we need to prove it under fire, a squeeze state receiver that potentially will bring us down below the quantum limit. I'm not an expert in that, but we have many experts here in this department about that whole technology. And that would be very exciting. The main drift of this thing is really not a lot of mass coverage. What we really want to do is actually produce technological nuggets that will be useful, and particularly the ADMX. It's a Ariadne. Andy Gerasi was a student of Kapitulnik at Stanford. It's a rotating, this is too big, it's a high-speed rotating thing with tungsten teeth, like this. There's a superconducting shield, and then there are these fancily shaped, actually, well, lens-shaped is important, polarized helium-3 things here read out by a squid, like this. And if there is a short-range interaction. They're able to look in conveniently from some few microns up to a millimeter like this. As these different masses spin by, you are able to induce a precession and a flip of the helium-3 and pick it up like that, synchronous with the rotational frequency. As you know, there's been a very beautiful class of experiments, sort of macroscopic torsion beams, polarized neutrons, and so forth, that have set very interesting limits on axions and other pseudoscalars in recent years. But this is a very beautifully designed experiment. If it works, it will actually come down and actually cut into the PQ band in a very interesting range, so 100 microeV to milli-eV range. Yes, in fact, you can. There are experiments that are done, not easy to do, where you actually look at in a magnet. You actually look at virtual. You see ordinary QED effects, but you can also look for effects of the axion mixing as well. Both of these effects can occur in a magnet. And the experiment you do there in a high-energy physics magnet is you launch in a laser at a 45-degree angle, and it turns out these two effects, this is your ordinary Delbruck here, 4-point diagram, plus axions, will lead to both birefringence and polarization rotation. QED only leads to birefringence, but the axion leads to both birefringence and rotation. And the reason is, of course, you've got two components here. This one, E parallel, and E perp. This one will get bleached out, and as it is foreshortened by a very, very, very tiny amount, then of course what you've done is you've tipped the vector over by some delta phi. But this is a really, really, really tiny number. It's sort of like the width of a human hair at the moon or something. It's a very tiny number. And this thing is so much bigger, and people have not even seen that one yet. That's the problem.
Okay, let's go back to Karl again.
I actually have a guest lecturer, so I have to make a cameo appearance, but I'm okay. So, good.
So I will email you about, say, the